Yeah, so hi, and this is for the nuclear and particle physics course, assignment 5, assignment 6, week 6. And today we will talk about the previous year question on the nuclear and particle physics of the week 6. So, this is the first question. Which of the following interactions are not influenced by electromagnetic interactions? And there are four options: E plus nu E to mu plus nu mu, E plus E minus to mu plus mu minus, E plus E minus to gamma gamma, E plus E minus to nu nu bar. So first of all, we need to check that all the four interactions are valid or not. Obviously, if it is not valid, then there is no question of getting electromagnetic or weak or strong interaction, right? So first of all, we need to check that it's the interaction whatever we are talking, that is that is valid, and after that we will check which type of interaction it is, right? So first of all, we will check first, like for any interaction to happen in nuclear physics, I just want to write a small general term here: to occur any nuclear reaction, okay, so to occur any nuclear reaction, we need to conserve three things at most. Okay, I mean, at the very first step, we need to check that these three interactions should be these three quantum number or these three conditions should be conserved in any type of nuclear reaction. The first one is what? First one is charge conservation. Second one is lepton number conservation. And the third one is baryon number conservation. So these three should conserve in any nuclear reaction, whether it is electromagnetic, whether it is weak, or whether it is a strong interaction. That does not depend on these three parameters. These three parameters should follow in each and every nuclear reaction, otherwise it will not gonna happen anymore. Okay, so first of all, for these four interactions, we have to first check that each and every interactions are valid or not. So just first, I'm just quickly checking that one, that it is valid or not. First of all, let's say A. For A interaction, in A interaction is what? I have told you that we need to check that charge, lepton number and baryon number. So charge is fine here. You can see E plus, that means plus 1, mu plus is plus 1. So plus 1, 0. As a whole, it will be fine. Now coming to lepton number. For lepton number case, let me write here E plus nu E going to mu plus nu mu. So for this interaction, it is valid or not, we have to check that by taking the Q value, that means charge. Charge is fine here, no problem. Now coming to lepton number. Lepton number, that means I am talking about each and every family lepton number should be separately and independently conserved. Okay. So what does this mean? This means that Le, L mu, L tau, all the three lepton number families should conserve separately as well as independently. So let's check Le first. Le for E plus is minus 1, for nu E it is plus 1, and for mu plus it is 0, it is 0. Now you can see that plus 1 minus 1, 0, 0, that is fine. For L mu, you can see this is 0, 0, and for this it is minus 1, this is plus 1. So as a whole, you can see that Le, L mu both are conserved here, and baryon, as these four particles are no longer baryon anymore, so that's why there is no baryon number problem at all. So you can see that interaction, whatever they have given us, E plus nu E going to mu plus nu mu, that is fine. I mean, like, that can be done. But in which interaction that can be done, that we have to search. In that question, maybe some of you came later, so I just came in the question again. Which of the following interactions are not influenced by electromagnetic interactions? So which interaction is influenced by which weak interaction, or electromagnetic interaction, or strong interaction? That depends on the mediator, right? So I will right now talk about to how to know that which interaction is mediated by which interaction, I mean governed by which interaction, right? So first of all, to see any nuclear interaction, nuclear interaction, and if it is a electromagnetic interaction or weak interaction or strong interaction, how do you know that, right? So first of all, for any type of EM interaction, if it is EM interaction, so what will happen? If it is electromagnetic interaction, EM interaction means electromagnetic interaction. So if it is electromagnetic interaction, then the mediator should be gamma. Gamma means photon. Okay? Photon. And at least one incoming particle has non-zero electric charge. Why I told you like that? At least one incoming particle has non-zero electric charge, because gamma is a one which will only interact with the non-zero electric charge particle. So obviously, if there is no charge particle, that means there is a neutral particle, so that will not interact with gamma directly. So mediator should be gamma, or mediator or the outgoing particle. Mediator or outgoing particle, if these two are gamma, then obviously without any doubt we can say that that is governed by electromagnetic interaction. So now by seeing these four interactions, we can see that obviously this C option is governed by EM interaction, because there is outgoing particle as gamma. So there is no doubt on that C, whatever it is, E plus E minus going to gamma, that is obviously a electromagnetic interaction. But what about others? In that other experiments, other nuclear reactions, we can't see gamma as a direct one. I mean, directly we can't see that where the gamma is present. So for that case, we have to check that, okay, let's say I am talking about B. B is what? B is E plus E minus going to mu plus mu minus. So I hope that Professor Pavlos have already told you about the Feynman diagram. So right now I will draw some Feynman diagram, so that it will be very easily you can understand that gamma is present or not in that interaction. So for this case, if I draw a Feynman diagram, then how the Feynman diagram will be? So it is, let's say, E plus E minus. Actually it should be like that because it's antiparticle, and the mediator is gamma. I told you there that, and then mu plus mu minus. Sorry, mu minus mu plus. Now you can see that in that expression, in that nuclear reaction, E plus E minus going to mu plus mu minus, as I mean, although we can't see from the direct by direct notation we can't see that gamma is present or not, but when we are talking about Feynman diagram, we can see that obviously as a mediator gamma is present here. So there is no problem on that. So B is electromagnetic. B is governed by electromagnetic. That means C plus B, E minus going to mu plus mu minus is governed by electromagnetic interaction. Okay, because the mediator is gamma here. I mean photon. And obviously in the C case, obviously we can see that the outgoing particle is as well a gamma itself. So obviously it is also governed by electromagnetic interaction. Now what about other two? I mean like A and D. There is something. Okay. So what about others? That means A and D. Sorry, yeah, A and D. A and D we have to check. So B and C both are electromagnetic. We have already checked that one, because for this case outgoing is gamma, for this case mediator is gamma. So B and C is electromagnetic. Now coming to A and D case. A and D case, you can see that for A and D, either in incoming or in the outgoing particle there is neutrino present. So if it is neutrino in the incoming as well as or in the outgoing particle, any type of, I mean like product particle will be neutrino or the incoming particle will be neutrino. If it is like that, then obviously without doing any mediator or any Feynman diagram, we can say that it is governed by weak interaction. Why? Because neutrinos only interact through weak interaction. So whenever neutrino will present in any nuclear reaction, that will be definitely 100% governed by weak interaction. Okay, so in that A and D option, you can see that our A has nu E as well as nu mu in the incoming as well as in outgoing particle, and for D option there is nu bar as an outgoing particle. So as the neutrino is directly present in that nuclear reaction, so that's why we can tell without saying any other things that A and B are governed by weak interaction. Okay. So to check it is weak interaction or not, first of all a very good idea is that we have to check if neutrino is present in that in the nuclear reaction or not. If neutrino will be present, that is obviously weak interaction by sure. But obviously there are so many weak interactions which are not governed by neutrino. For that case, what we need to check? We need to check some other things, like we have to check the strangeness quantum number. It should not be violated. It should be violated, and something like that. But if it is the neutrino, then obviously directly it will be a weak interaction. Now coming to strong interaction, how do you understand that what is strong interaction or not? For strong interaction, most probably, I can tell you most probably all the strange particle will participate. Strange particle will participate means strange particle means where, I mean the particles which has a non-zero strangeness quantum number. Either it will be +1 or it will be -1, +2, -2, -3, or all these things. But if it is a non-zero strangeness quantum number, that means the particle is strange particle. So most of the cases, not obviously all the cases, but most of the cases, all strange particle are participate in strong interaction. And for strong interaction, the main criteria is that the delta S should be 0, right? So delta S should be 0 for the strong interaction. So we have to check that one also. But for this question, whatever we were talking about, there you can see directly that in option number C, gamma is present directly. So obviously it will be electromagnetic. For option number B, we have done the Feynman diagram, and after that we have seen that gamma is present at the mediator. A and D, both these two has neutrinos, so obviously it will be governed by weak interaction. Okay. So which of the following interactions are not influenced by electromagnetic interactions? That means A and D will not influenced by electromagnetic interaction, because these two are governed by weak interaction only. Okay, so this is the first question. Maybe it's understandable. I'm audible, right? Yes? Can anyone confirm me I'm audible or not?
Yes, ma'am, audible.
Okay, fine. Okay, so this is the case. Now coming to the second question, which of the following interactions are influenced by electromagnetic interaction? Now see, they are asking that influenced by electromagnetic interaction. So obviously, as I told you, for electromagnetic interaction case, we have to check that gamma is present or not, like as an outgoing particle gamma is present or as a mediator gamma is present. So obviously from the four options, I can definitely say that this is EM interaction, because the gamma is a outgoing particle. Now coming to B. In that case also, just I did that one, right? E plus E minus going to mu plus mu minus. So here also you can see that that is also governed by weak interaction, electromagnetic interaction, because the Feynman diagram was like that: E plus E minus, mediator was gamma, and then mu plus mu minus, right? So this is the case. So obviously for the B option also, it is governed by electromagnetic interaction, and obviously you can see that for the D case it is weak interaction, because as I told you, here neutrino is present and neutrino only interact with weak interaction. So obviously if neutrino is present, that means it will be in weak interaction. Now one more is left, that means E plus U going to E plus U. Now let me do that one. What it will be? E plus U going to E plus U. So this one. So this one, how to calculate this one? I mean, how to know that which interaction will govern? here. First of all, maybe gamma should be there, maybe. Okay, one thing is that maybe gamma will be as a mediator, because you can see that, okay, gamma means obviously gamma does not have any charge, so whatever the initial particle was there, that will be the same as final particle, otherwise gamma will not be the mediator, right? Okay, so gamma can be a mediator for this, can be, but we have to check by drawing the Feynman diagram. Okay, now one more thing is that as I told you that gamma only interact with the charged particle. So here E plus is also charged particle, U is also a charged particle. For U the charge is like plus 2 by 3 into E. So this is also a charged particle, E plus is also charged particle. So possibly E plus U going to E plus U can be governed by weak interaction, electromagnetic interaction. Now we have to check the Feynman diagram to confirm that it is weak electromagnetic interaction or not. So how to check that? First of all, U, E plus U. So one interaction will be like that, E plus, right, E plus, then U, okay, I'm just writing right now, and after that I will tell how I can write. So I am talking about this as a time direction, and this is gamma. So what does this mean? This means that E plus is coming, U is coming through through gamma, it is mediated, and after that the E is coming out, I mean E plus is coming out and U is coming out. So obviously the representation of this interaction is nothing but E plus U going to E plus U, right? And you can see that in this vertex U as a outgoing, incoming, outgoing, so, and this is the gamma, so charge is conserved. For this vertex also the charge is conserved, no problem on that. So this interaction can be possible through the Feynman diagram consideration. So this is nothing but here the mediator is gamma, right? So that's why we can tell that this interaction E plus U going to E plus U, that can be mediated by electromagnetic interaction. Okay. So which of the following interactions are influenced by electromagnetic interactions? So this one is EM interaction, as from the Feynman diagram we can see that, and this one is also weak interaction. This one is electromagnetic interaction. This is also obviously electromagnetic interaction, because gamma is present as the outgoing particle, and here also gamma is present, here also gamma is present. Okay, by the way, just don't confuse with gamma and nu. Gamma is like that and nu is like that. Okay, I mean this is your convenience how you will mention that. So the main thing is that, so electromagnetic interaction influenced by electromagnetic interaction, the answer will be A, B as well as C, because these whole three options are governed by electromagnetic interactions, and this one is obviously governed by weak interaction, because the neutrino is present here. Okay, so this is the case. So the answer for this question will be A, B and C. These three are influenced by electromagnetic interactions. Okay, so maybe we can go to the next question. Where is the next question? The next question is the decay of delta minus goes to pi minus pi 0 is not permitted because of which reason? Okay, so delta minus going to pi minus pi 0. First of all, I told just right before some time that to occur any type of nuclear reaction, we have to see three fundamental quantum charges to conserve. One is charge, another is lepton number, and another one is baryon number. So these three should be conserved in any nuclear reaction. If these three are not, among these three, if at least one will not conserve, that means the nuclear reaction will not gonna happen. Okay. So now we will just check that one right now. Very first, delta minus going to pi minus pi 0. So Q Q is -1, -1, 0. So Q is fine here. Now coming to lepton number. Obviously delta minus pi 0, none of them are lepton. So that means that will be only 0, 0, 0. That is also fine. Now coming to baryon. Delta minus is a baryon, right? So delta minus has a baryon 1. Pi is not a baryon, it is a meson. So that means it will be 0, it will be 0. Now you can see that our delta B is not equals to 0. That means our delta B is equals to 1, which tells us that our baryon number is violated in that nuclear reaction. So if the baryon number is violated, so obviously it will not gonna happen. Okay. So the decay of these is not permitted, because of which reason? So obviously we can see that the reason will be non-conservation of baryon number. Now you can ask me one thing, that energetic reason. So we should see that one also, because in any nuclear reaction energy should be conserved by any chance. That is obviously fine, but most of the time we can't remember the mass as well as the energy of this particle, right? So by seeing the lepton number or baryon number or electric charge, we have to check that it is going to happen or not. So delta minus going to pi 0, for this nuclear reaction it will not gonna happen, because non-conservation of baryon number. Delta minus is a baryon, but pi 0 is not a baryon particle. These are the meson particle. So that's why. Energetic reason is also there, but yeah, fine, that is not that much problematic. But this case energy is not that much problematic, but for this case baryon number is very much problematic. Okay, so this is the thing. This one I have written here, but we will talk later for this case. Just try to remember this thing, that delta particle has the mass 1232 MeV, pi has a mass 140 MeV, and neutron has mass 939 MeV. Why I have written here? Just to remember that sense that energy conservation should be there in any nuclear reaction. But obviously, again and again I am telling, before going to see the energy conservation, we have to first check that charge, lepton number and baryon number, these three are conserved or not. If any one of them are not conserved, that means it will not gonna happen anymore. Okay. And obviously if these three are happening, I mean if these three are very much satisfying, then we can check for the energy and momentum, I mean energy momentum conservation or energy conservation, mass conservation, that things we can check. But for this case, obviously, as you said, I mean as you see that there is baryon number problem, so obviously it is not going to happen. Okay. So question number 5 or 4. The decay of delta minus going to pi minus n is permitted or not permitted? That they are asking. Okay, so first of all, delta minus going to pi minus n. As I told you at the very first, we will check charge. Charge is -1, -1, 0. Very good. Lepton number. This is not lepton, not lepton, not lepton. Very good. Now coming to baryon number. This is baryon, this is not baryon, but this is baryon, because neutron is a baryon number, baryonic particle. So that is also fine. Delta B is equals to 0. Now you can see that charge, lepton and baryon, these three are fine here. I mean these three are conserved in that reaction, delta minus going to pi minus plus n. So now the second question is that, is it permitted or not? So as these three are already satisfied, then after that we will check the energy conservation. Okay. To see the energy conservation, pi minus plus n. So for energy conservation, we have to see the mass. Mass of delta minus should be greater than or equal to mass of pi minus plus mass of n. Yes, because obviously to have any decay, the incoming particle mass should be greater than the outgoing particles mass. So now check, as I told right now, that mass of delta is 1232 MeV. Mass of pi is 140 MeV. Mass of neutron is 939 MeV. Just add these two, 140 plus 939. How much it will be? This one. Okay. Right. So now you can see 1079. This number is less than 1232. Whatever the condition for mass conservation was there, m delta minus greater than or equal to m pi minus plus m n, that is conserved here, because here it is 1232 and this is 1079, and obviously 1232 is greater than 1079. So I can see that energy is conserved. I mean, energy perspective, it is fine. Charge is fine. Lepton number is fine. Baryon number is fine. Now see the options. Not permitted energy reasons. No, it's not correct. Not permitted because of non-conservation of lepton number. That is also not correct. Not permitted because of non-conservation of electric charge. That is also not correct. So that means it is permitted. Okay. So the option will be B. If you have any doubt, you can ask me in any step. There is no problem. Okay, so as these are very simple things, so that's why maybe we can go very quickly also. But yeah, obviously whenever you will have problem, you can ask me. Now see the question number 5. Which of the following reactions are not allowed? Not allowed, okay? Just see the question first. Which are not allowed? Let me write the first expression. I mean, one by one we will write. This one is first one right now. Yes. So for this case, as we all told, these three should be conserved in any case. So let me write here Q. Q is plus 2, 1, 1. Fine. L. This is not lepton, but this is a lepton with minus 1 because it is mu plus. Mu minus will give the lepton number as plus 1. Mu minus will give as minus 1. This is also not a lepton. So that means it will not gonna happen anymore. Now coming to baryon also, but obviously if lepton number is not conserved, then we don't need to go for the baryon number, but still for the completeness we are checking that one. Baryon is fine. This is 1. This is not baryon. This is also not baryon. So that is also not gonna happen. Now for this reason you can say that this is not gonna happen anymore. Delta plus plus going to pi plus pi mu plus. So this is which of the following reactions are not allowed? A is not allowed. Now coming to B. P plus pi plus. Okay. P plus pi plus. Charge 2, 1, 1. Fine. L. None of them are lepton, right? Fine. Baryon. This is baryon. This is also baryon because this is proton. This is not baryon. That is also fine. So now for the QLB, these three are satisfied. Now coming to mass. Delta has the mass 1232. P has a mass 938. Pi plus has a mass 140. Okay. So as a whole, how much it will be? It will be like 7, 10. So that is also fine that 1232 is greater than 1078. So energy is also fine. Now coming to strangeness. For this case, this is not a strange particle. This is not a strange particle, this is not a strange particle. So this is also gonna happen. So as you can see from the very layman language that Q, L, B, S as well as mass, energy conservation, all the quantum charges, quantum parameters are conserved here. So that is going to happen. So it is not allowed, it is allowed. Now coming to C, delta plus plus mu plus E plus. Okay. Can anyone tell me, is it allowed or not? If it is not allowed, then by which section I can tell that that is not allowed? Can anyone tell me? I mean, what is the problem in that nuclear reaction which will be violated here? Delta plus plus going to mu plus E plus.
Ma'am, baryon number 100.
Yes, baryon number 1, this is 0, this is 0. So obviously if baryon number is not 0, so obviously we will not check any more other things. So baryon number is very violated here. So baryon number is violated. Let's check for the completeness lepton number. Obviously lepton number means Le, L mu both we have to check. For Le this is 0. For Le this is also 0. For Le this is minus 1. That is also not gonna happen. L mu this is also 0. For L mu it is minus 1. For E plus L mu is 0. So this is also not conserved. So obviously like Le L mu we should not check because we have already checked that baryon number is not conserved. So obviously this interaction is not going to happen. So this is not allowed. Okay. Now delta plus pi minus pi 0. That is also very simple to see. But still, like if you have any doubt, obviously we can see that one also. Pi plus pi minus pi 0. No, delta, what was it? Delta plus plus, okay. That is at the very first this charge is not gonna happen to conserve. This is 2, this is 1, this is minus 1, this is 0. So charge is already, and at the very first charge is not conserved. So if charge is not conserved, there is no question to go other things. So this is also fine. So which of the following reactions are not allowed? Not allowed means 1, C, A, C and D. Okay. So, yeah, this is question number 5. Now coming to question number 6. Which of the following reactions are allowed? Similar question. So maybe we can go quickly also for that. Mu plus pi 0. Q, B, L. Q, 1, 1, 0. Baryon. This is baryon. This is lepton. This is also meson. So it is not. So that means this is not allowed. Now pi plus p plus. I think it's already done. Delta plus plus going to p plus plus pi plus. We saw that this is allowed, right? Just before some time we saw that one. Again also I can write that one also. This is 2, 1, 1, 0, 0, 0, 1, 1, 0. And for mass is also fine. 1, 2, 3, 2. This is 938. This is 140. All the things are in MeV unit. So that is also fine. Then strangeness is also fine. 0, 0, 0. So that is allowed. So this is allowed. Now delta minus going to mu minus plus n. Delta minus going to mu minus plus n. What is the problem here? Can anyone tell me quickly? Baryon number is fine or not? This is baryon. This is not baryon. This is baryon. So that is also fine. That is also fine. What about lepton number? Let's say L mu I am talking. This is 0. This is my 1 because mu minus is there. Mu minus has lepton number plus 1. For n, lepton number is not non-zero because it's a non-lepton particle. It's a baryon particle. So for that case, delta L mu is not equals to 0. Okay. So if lepton number is not conserved here, that means it is not allowed. Now again delta plus pi plus pi minus pi 0, that is also not gonna happen because of Q. Maybe I can write here that what is the reason behind that. The lepton number is problematic. Actually L mu is problematic. Here baryon number is problematic. And this is allowed. So which of the following reactions are allowed? So that means A is not allowed. Only B is allowed here. Okay. So the main take home message for all the questions are right now that charge, lepton number, baryon number, these three should be conserved in any nuclear reaction. And after that, obviously we have to check that mass of the particle, mass of the incoming particle should be greater than or equal to outgoing particles mass summation. And if any of these terms like Q, L or B, if any of them are not conserved, then the nuclear reaction is not gonna happen anymore. So these 4 or 5 points are the take home message up to this question number 6. Okay. And one more thing was there, if which interaction it is, to know the which interaction it is, we have to check that what will be the mediator or what is the outgoing particle for that nuclear reaction. If the outgoing particle is gamma, that means photon, so obviously that will be governed by electromagnetic interaction. If the mediator is gamma, that is also governed by electromagnetic interaction. If the neutrino is present in any nuclear reaction, that is obviously weak interaction, because neutrinos only interact through weak interaction. And for strong interaction, we have to check that the strange particle will be there or not, and the strangeness quantum number should be conserved for strong interaction. So these points we have to remember, and accordingly we will answer the questions. Okay. Okay, so up to this maybe it's fine for everyone. Now we can go to the question number 7. If you have any doubt, any type of doubt, you can ask me. Question number 7. Choose all the correct statements from below. What are the statements? Top quark is the heaviest elementary particle known to us. Discovered so far. Baryons are made of two quarks. Under suitable conditions, electron and positron can form bound states. Gluons can directly interact with photons. So these 4 options are given here. First of all, I want to tell there are how many quarks are there till now. Till now there are 6 quarks, right? U, D, S, C, B, T. Up quark, down quark, strange quark, chum quark, bottom quark, top quark. So among these 6 till now, these 6 are discovered so far. So among these 6 quarks, if I see the mass of these 6 quarks, then the mass of the top quark is the highest one. It has the masses of the order of 170 GeV, if I am not wrong that much. 170 or 175 GeV or something like that. Okay, just check that one, but it's obviously the highest mass among all the other quarks as well as all the elementary particles known to us. Okay, so top quark has the highest mass. So this one is fine, correct. Baryons are made of 2 quarks. Obviously this is not right, because Baryon is nothing but q q q. For meson it is q q bar. So for baryon q q q is there, so that means for to have it is a baryon 3, minimum 3, not obviously minimum 3 baryon quarks should be present here, and for meson 2 quarks should be present, one is quark and another one is anti-quark. So baryon, whatever it is written, baryons are made of 2 quarks, that is not correct, that is wrong. Now coming to C option, under suitable conditions electron and positron can form bound states. So electron and positron, E plus, E minus, they are going to form a bound state. Yes, this is correct. The bound state is known as positronium. Okay, so at which condition it is gonna make a positronium? Electron and positron can make a bound state known by positronium. Positronium can form in a vacuum, and its formation is often observed when positrons slow down after being emitted from a radioactive source and interact with electrons in a material or in a gas. So it's not gonna happen that if it is E plus and if it is E minus, then always E plus and E minus going to annihilate and it will make a gamma, 2 gamma. It is not always possible. Obviously most of the cases E plus and E minus is going to annihilate, and after that the proton will form in most of the cases, but still in some specific cases, if I have some suitable condition, under suitable condition, we can make E plus as well as E minus to make a to make a bound state, and the bound state is known as positronium. So what is the condition for that? I wrote here. Positronium can form in a vacuum also, and its formation is often observed. When the positronium bound state will observe, it will observe when positrons, positronium, right? Positronium will observe when the positrons slow down after being emitted from a radioactive source. One radioactive source is there, from there one E plus is coming out, and that is interacted with E minus in a material or in a gas. So E minus, where it is present? It is present in a material or in a gas, and in that condition one E plus is coming out from the radioactive source. So in that sense, one E plus is coming out, this E plus will interact with E minus, and this will make one positronium bound state. Okay, so this is the thing, positronium bound state. So whatever the option was there, this is correct. Gluons can directly interact with photons. It is correct or not? That is a very good and interesting question. Gluon. Gluon is what? Gluon is the mediator for strong interaction, right? And for strong interaction, what is needed? The main thing needed is color charge. Okay? So gluon has color charge, non-zero color charge, but it does not have non-zero electric charge. There are some differences between this electric charge, baryon charge, lepton charge, quark charge, color charge, all these things. Previously, when we will not talk about nuclear particles physics, we will only talk about simple physics. Then there we are talking about charge. Charge means it is always an electric charge. But right now, in particle physics, there are so many charges. Electric charge, then color charge, then there are so many quantum numbers, lepton number, quantum number, baryon quantum number. Even also, sometimes some people are telling lepton number as lepton charge, baryon number as baryon charge, something like that. So, for gluon, there is no electric charge. This is neutral. in the concept of electric charge, but they have color charge. Why they have color charge? Because they are interacting, mediator, they are the mediator for strong interaction. And for strong interaction, obviously the particles have the colored charge, so obviously gluon should have the color charge. So gluon have color charge. Gluon do not carry electric charge, they carry color charge only. Decidedly, photon on the other hand interact with electrically charged particles but do not have any direct interaction with color charge. Therefore, in the standard model of particles, gluons and photons do not directly interact. Obviously, there is some indirect interaction between gluon and photon, but right now we will not talk about that one. We will only focus that gluons do not directly interact with photon. Okay, so gluon cannot directly interact with photon. So gluons can directly interact with photons, that is wrong. So among these four options, we can see A and C is correct. This is question number 7. Any doubt up to question number 7? Or maybe we can go to question number 8. Okay, question number 8. E minus going to mu minus plus nu mu bar plus nu e. Decay is not allowed because of which? Mu minus nu mu bar nu e. First of all, just check Q. Minus 1, minus 1, 0, 0. Fine. Baryon number, none of them are baryon. So 0, 0, 0, 0. That is also fine. Now come to lepton number. Mu mu bar mu e. Okay. Lepton number. Lepton number means Le. Le for my E minus, it is 1. Mu minus 0, nu mu bar 0, nu e 1. So Le is also fine. Delta of Le is 0. L mu 0. For mu minus it is 1. For nu mu bar it is minus 1 and this is 0. That is also fine because plus 1 minus 1 0 and in the left hand side it is 0. So L mu is also fine. Now we can see that Q, B, Le, L mu, L tau. Okay, let's check L tau also. As there is no tau particle, so that is also fine. So Le, L mu, L tau, B, Q, all the Q, B, Le, L mu, L tau, all are conserved. Okay. So apparently we can see that there is no problem in that nuclear reaction. But obviously, as I told you, that after that we have to check the mass conservation. Now check mass. Mass of E, mass of mu, mass of nu mu, mass of nu e. So what is the mass of Me? 0.511 MeV. What is this one? This is of the order of 105 MeV. This is of the order of 0. This is of the order of 0. Now you can see Me is very less than mu. So in rest case, if electron is at rest, it cannot decay to mu, nu mu bar, nu e because of the mass problem. Now someone can ask me if let's say I have a very energetic electron and after that we are going to do that interaction, that can be possible because as a whole, if it is a kinetic, if the kinetic energy of the electron is such that the kinetic energy plus rest mass energy of the incoming particle is greater than or equal to kinetic energy and kinetic energy and rest mass of outgoing particles, then the process is happening. But as right now we don't have any information that E minus is in the motion and it has a very high kinetic energy, we will take in assumption that E minus is at rest, and if E minus is at rest, it is not gonna happen anymore because of the energy problem. Okay, so the correct answer will be energetic reason. All other problem are there is no other problem. Baryon number is conserved, lepton number conserved, electric charge is also conserved, but the main problem is energy. E minus cannot go to mu minus plus mu bar plus nu E, as mass of electron is much less than mass of mu, and mass of mu mass of nu E are of the order of 0. Okay, so that's why we will not talk about that one, but as this one is smaller than this one, so this is not happening. Okay, this is question number 8. Now we can go to question number 9. Okay, so this is question number 9. P is going to N E plus nu E. Decay is not allowed because of what? P N E plus nu E. First of all, Q 1 0 1 0. Baryon, this is baryon, this is baryon, this is lepton, this is lepton. Le, why? Because there is only E particle is there, so this is 0, this is 0. For E plus, Le is minus 1, for nu E, Le is plus 1. So now you can see that Q, B, Le as well as L mu, L tau, all the things will be conserved. How? Because obviously L mu, L tau case, mu should be there, but here in the incoming as well as outgoing particle, mu type particle is not present, so that's why L mu is not gonna problematic. L tau is the same thing, so L tau is also conserved here. Now check the mass. P going to N E plus nu E. So mass of proton is 938 MeV. Mass of neutron 939 MeV. Mass of E plus 0.511 MeV. Mass of nu E of the order of 0 MeV. So now you can see 938 is in the left hand side. In the right hand side it is 939 plus 0.511. So that is obviously greater than this one. So as MP is less than Mn plus Me plus M nu E, this interaction is not happening in rest case, in rest proton. So the decay is not allowed because of the energetic reasons. Okay. So this is also very simple to understand. Now maybe we can go to the next question. This one. Which of the following pairs have identical valence quark content? So the valence quark is like, which of the following pairs have identical valence quark content? So there are 4 options. So there are four options. One is a neutron delta lambda 0, then proton delta plus, and the C option is lambda 0 sigma 0, and the fourth option is pi minus mu minus. Okay. So first of all we need to check D. D option is what? Pi minus mu minus. Pi is a meson, but mu minus is a lepton. So as this is a lepton, so this is itself a elementary particle. Okay, so if it is a itself a elementary particle, that means there is no quark content inside of that. So that option number D is not gonna happen anymore. Okay, so this is wrong. Now coming to she. She is lambda 0 sigma 0. Obviously lambda as well as sigma both are baryon. So there may be a chance that these two have the same quark number, quark content. Okay, from the outgoing thing we can see that lambda 0 sigma 0 both are chargeless, electric chargeless. That means whatever the quark content will be there will be no charge, net charge of this particle. So maybe that will be the one to have these two as a same quark content. Now what is the quark content for lambda 0? What is the quark content for sigma 0? Lambda 0 has the quark content UD-ish. Sigma 0 is also have the quark content UD-ish. Why? The strangeness for lambda 0 is -1. Strangeness for sigma 0 is also -1. Now -1 is coming from which sense? We know that if one strange particle is present, that means one strange quark is present in any particle, S, that means strangeness quantum number, will be -1 corresponding to that particle, right? So in that case you can see UD-ish. U is not a strange particle, D is not a strange quark, but S is a strange quark. Strange quark means it has the strangeness quantum number as a -1. So UDS, that will give a strangeness quantum number -1 for lambda 0. For sigma 0 also it will be a -1 because it is also a UDS. One more thing is that lambda 0 sigma 0 both are present here. This is sigma minus, this is sigma 0, this is sigma plus, and this is lambda 0. So what is this? This is like octet, baryon octet and decaplet is there, na? So there is a symmetry between Y3 and I3 and Y, sorry, I3 and Y, and after that, after putting all these particles in that I3 and Y plot, we can have a baryon octet, baryon decaplet. In that baryon octet, if I just see the nature, this will be sigma minus, this is sigma 0, this is sigma plus, and there is again at the same position lambda 0 is present. So that means the quark content for sigma 0 and lambda 0 are exactly same, UD-ish. Okay, so these has same. Now B, P and delta plus, P delta plus. First of all, just check Q. Q is also 1, Q is also 1. So that means maybe it will be the same one. Okay. Now strangeness. Both are strange, no strange particle is present at all. Because this is also strangeless particle, this is also strangeless particle. So the strangeness quantum number for P is 0, strangeness quantum number for delta plus is also 0. Both are baryon, so that is also fine. Now coming to the quark content. For P, the quark content is UUD. We all know these things. UUD and UDD is a neutron. For delta plus, the very quark content is also UUD. How we can say that? We can say from these things. There is I3Y plot I told. So here, if it is octet, for octet case it is like P and N. So P is like UUD. Same thing is happening for this. Why? I3. I3 and this is decaplet and delta, what is that? Delta plus. So delta plus is where this is delta minus, delta 0, delta plus, delta plus plus. So delta plus is also there, and delta plus is having the same y and I3 value. P is also having the same y and I3 value, and it has the same quark content as UUD as P. So P and delta plus both are having the same quark content as UUD. That means this is correct. Now coming to N and lambda 0. N lambda 0. Okay, for baryon number conservation both are baryon. Charge conservation both are chargeless. That is fine. Strangeness number both are both are not strange particle. That is also fine. But delta 0 has UDS. No. Delta 0 has, I also forget right now what is the quark content for delta 0. I have already mentioned here somewhere maybe. Maybe I did not write here delta 0, but delta 0 and N is UDD, right? N is UDD and delta 0. Just check y and I3 value, that is also not gonna match, I think. So N has this one. This is P, this is N, and I3, and this is half, this is minus half. Actually it will be N and P, whatever, N and P. This is minus half, this is plus half. So this is minus half, and y value is, y value we can find from that value also, no problem. So I3 is minus half here for delta, and it is like UDD, right? Similarly for delta, delta plus was there, and this is delta minus, delta 0, delta plus, delta plus plus. So there are 4 members in that group. So it is like minus 2, minus 1, 0, oh no, minus 3 by 2, minus half, 0, half, 3 by 2. So this is also minus half. So we have to check the delta 0 quark content. I think delta 0 quark content is the same one. Sorry, but I forgot the delta 0 quark content right now. Delta particle quark content. Let me check, because all the things are matching here also. yi3 value is also matching, then it is also UDD. So delta 0 is also UDD, because you can see that I3 and y value are also matching here from the decaplet as well as octet. This is also for UDD, it is also UDD. So obviously this is also same. I was forgetting that one, but yeah, fine. So this is also same. So now we can see that A, B, C, these pairs have identical valence quark content. So N lambda 0, P delta plus, oh sorry, this is lambda 0, sorry, this is lambda 0, I did not see that. If it is lambda 0, then it is not gonna same, because lambda 0 is only one particle which is present here. Just see, we were talking that lambda 0 and sigma 0. So lambda 0 is sigma 0 are the same, which has the UDS, and the strangeness number is also 1, sorry, minus 1. So lambda 0 has a quark content UDS, but n has UDD. So obviously this is UDS. So n and lambda 0 is not same as quark content. I thought that it is delta 0. Delta 0 will be same, but lambda 0 is there, so lambda 0 is not gonna same. Okay, so sorry for that inconvenience. This is lambda 0. This does not have same, not has same quark content. Okay, so this is not same. This is UDD and this is UDS. Strangeness is 0, strangeness is minus 1 for this, and lambda 0 is present here. Here is lambda 0 in the middle of the octet. So this is not happening. Okay, so this is not correct. So B and C are the identical valence quark content. Okay, I did not see that it is lambda 0. Obviously it is lambda 0, that means it is not same. Okay, so maybe we can go to the next question number 11. If you have any doubt, you can ask me in between that also. In the decay of delta minus going to n plus something, the missing particle is what? It's interesting. Delta minus going to n plus something. So what is something here? To know the something, we need to check Q, B and L at the very first, right? Because this is decay and this is gonna happen anymore. So that means obviously if it is happening, that means there will be something which will conserve Q, L and B, all the quantum charges, as well as the strangeness is also conserving, but we will check later that one. But for Q is minus 1, this is 0. So whatever the particle will be there, the charge will be minus 1 for this, right? Lepton, this is not lepton, this is not lepton, so obviously the particle will not be a lepton. Baryon, this is one baryon, this is baryon, so this particle is also not gonna baryon because 1 is already there. So lepton is not, this particle is not a lepton, this particle is not a baryon, from these three things. And one more thing is that the particle will have a charge minus 1. These three conditions we got. So based upon these three conditions, can we conclude the particle's identity? Okay, let's check. Neutron does not have any charge, but electric charge, but they are telling that the electric charge of the missing particle should be minus 1, so it is not correct. Pi minus have electric charge minus 1, that is fine. It is not a lepton, that is also fine. It is not a baryon, that is also fine. So pi minus can be. Now coming to proton has plus 1 charge. They are saying it is minus 1 charge, so it is not correct. E minus has minus 1 charge, that is fine. But for lepton case, electron is a lepton, so it is also not gonna correct one. So the correct one is pi minus. Okay, is it understandable? I am explaining these things very simplified manner as well as very slowly so that you can understand clearly. So to know the missing particle, we need to check Q, L, B at the very first, and which one is matching these three conditions, that one will be the correct option. Okay, so from this pi minus is the correct one. Till now there is any question, any doubt, anything? Let me know. Okay, so whatever I was talking till now, I have made a table of that, that to know the all the answer regarding the elementary particle physics questions, we just need to remember some of the particles, charge, strangeness number, IP configuration. Like photon, I have just mentioned here, I have just tabulated here. Particle is there, then I means that total quantum number, spin quantum number. Then Jp is the total quantum number. Sorry, I is isospin. Sorry, I is isospin. And Jp, P is parity, and J is the total angular momentum quantum number. Charge is there, S is there. S means strangeness quantum number. So I have just mentioned here. Obviously, this table is not a complete one. There are so many particles other than that one also, but I have mentioned here because in most of the elementary particle physics questions, these particles are present in the question. So that's why I just mentioned these particles: charge, S, I, Jp value. So these are the things you can check that, as well as the particle for the lepton case. Lepton is also there. I just mentioned here for the lepton. And this is the quark constituents. After that, the particle is what, and then Q value, Y, B, S, I3. And if I3 is there, then you can obviously say that what will be I, right? So this is the thing. Okay, now coming to the last question, maybe in the decay of delta plus going to pi plus plus Misching. What is the Misching particle? Delta plus pi plus plus Misching. First of all, charge 1, 1, 0. So that will be a chargeless particle. Lepton number 0, 0. So it is it is not a lepton particle. Baryon number. This is baryon. This is not baryon. So this should be a baryon. Right? So among these three, we can confirm that the particle is a baryon with Q as 0. Okay? Now check these four options. Neutron as a baryon. Yes, neutron is a baryon. Pi 0 is not a baryon. Obviously, it's cut. Proton is a baryon, but it does not have Q equals to 0. So that is not fine. Delta 0. Delta 0 is also a baryon with charge Q as 0. That is also fine. So An and delta 0, these two can be possible candidate. Now what we will check next? We will check next the mass conservation. So delta plus going to pi plus plus something. We are having two options. One is neutron and another one is delta 0. Now coming to first option, neutron. Delta plus going to pi plus plus neutron. What will happen for this case? In the concept of mass is 1232 for delta plus. For pi plus it is 140. For n it is 939. So if I add these two, then it will be like 7, 10, 1079. It is less than 1232. So that is fine in terms of energy momentum conservation. Now coming to delta 0. If delta 0 is the particle, then delta plus going to pi plus plus delta 0. Delta plus has mass 1232. Pi plus has mass 140. Delta plus is also have the mass 1232. Obviously there is a little bit little bit difference from 1232, but nearly 1232. Okay. But if I add these two, that is greater than this one. So that is not correct from the energy momentum conservation law. point of view, right? So the delta zero option is not happening due to energy momentum conservation. Actually it should be a energy conservation only, mass conservation I should write. And so the answer will be neutron. So I think this is the last question for today's session. Yes. So does anybody have any doubt on any question? I'm just going to show you from the very beginning what were the questions, 12 questions, so that you can remember and you can ask me if there is any question. Okay. The first question was, the first question is this one: which one is not influenced by electromagnetic interaction? And the answer is A and D. Second question is, which of the following are influenced by electromagnetic interaction? This is A, B and C. A, B and C. Third question is, decay of delta minus going to pi minus pi 0 is not permitted because of which reaction, which reason? Fourth one is, delta minus going to pi minus n is permitted or not permitted? Which of the following reactions are not allowed? And the answer is A, C and D. Which of the following reactions are allowed? And the answer is allowed, B. Okay. And this is also, this is B, only B.